All right, good morning, everyone. My name is Ben Fisher. With me today are Andrew Bosford, our transportation engineer, Dana Fish, our environmental lead, and Hunter Neifel, our water resources engineer, and then I'm our project manager and structural engineer. Going straight into transportation, I'll give it to Andrew Bosford.
Thank you. Let me first begin by going over my scope for the last time. We're designing 2 roads, a walking trail, a parking lot for a senior living facility. Moving on to the design criteria. Everything has been designed in accordance with the Astro Green Book, the in-depth design manual, got Americans with Disabilities Act, and then lastly, any city developers ordinances. First, we got Bill Park Road. We got 3 lanes, all 12 foot wide. Got east, westbound, and then a lane in the middle to turn left and right from. And then the walking trail is running on the north side of the road. Next, we have Old Oak Drive. We got 2 11-foot lanes, north and southbound, and then 4-foot shoulders, which seems like a lot, but we wanted to be able to accommodate emergency vehicles. Next, we have the intersection. It is a stop control with Old Oak yielding to Bill Park Road. Next, moving on, we have the parking lot, which has 45 standard spaces. You have 4 disabled spaces and then 2 van loading, which is more than what's required, but for a senior living facility, we like to have just extra accommodations, especially with disabled vehicle slots. Moving on, we have the cross section. As you can see, we have the 12-foot wide lanes and 4-foot shoulders on both roads. And then on the Bill Park Road, you can see the walking trails on both sides of the road. So we got the cost estimation. One thing to note for the culvert, that was not a part of my scope, nor was it the water resources, so we had to get a quote for the culvert, and it was, we sent it out, and we got a quote back for $150,000 for a total of $3.2 million for transportation. Now moving on to water resources.
Hi, I'm Hunter. I'll talk about water resources. So to begin, the final design will fulfill all of the scope requirements previously discussed. The figure to the right shows the design with the roadway portion utilizing vegetated swales to treat water quality with a dry pond used for flood control. The building plot utilizes 2 rain gardens for water quality, and they drain to a wet pond for flood control. Upturned elbows in the rain gardens and floating treatment wetlands in the wet pond will provide sufficient nitrogen removal. So the main water quality BMP for the building plot is the rain garden. As previously mentioned, there are 2, one to the east and one to the west, providing 851 and 2,891 cubic feet of water quality storage volume, respectively. The figure shows a typical cross-section of the rain garden, which is going to be used with 4 feet of plant soil depth, followed by 4 inches of wash stone, and then 8 inches of number 57 stone. A 4-inch pipe under drain with an upturned elbow is used to allow for denitrification to occur and nitrogen to be removed from stormwater runoff. The floating treatment wetlands will be installed in the building plot's wet pond. Using strategic placement, less surface coverage is required. The figure shows the 75 floating treatment wetlands necessary in order to achieve 5% surface coverage. And the 5-foot by 5-foot floating treatment modules can be connected and inferred in order to form this pattern shown on the water surface. Moving on to the roadway portion with the vegetated swale. It was initially designed for water quality treatment and the 3-month, 24-hour storm. The city of Valparaiso requires limits a maximum depth of 4 inches, along with side slopes 4 to 1 horizontal to vertical, and then a maximum water velocity of 0.9 feet per second. So the 5-foot bottom width on the swale provides enough area for water hurricane to occur. So the swale was also designed for flood control in the 100-year 24-hour storm. And after flood control analysis, the depth of the swale came out to be 1.25 feet and allowing for 6 inches of freeboard. The total depth of the swale was 1.75 feet. Additionally, check dams will be used to slow the water velocity and to also provide a water quality storage volume. Timber check dams with a 9-inch height will be spaced at 37.5 feet, and riprap will be installed behind in order to prevent erosion from flowing water. To begin detention pond design, an inflow hydrograph, as seen in blue, was produced using the WinTR55 computer program. Next, the maximum allowable release rate was determined through the City of Valparaiso regulated release rate of 0.5 cubic feet per second per acre of developed land. And then finally, the outflow, as seen in orange, or an outlet structure was selected, and level pole routing was performed to produce the outflow, as seen in orange, and it was made sure that it was less than the maximum allowable outflow. And the same process was used for both the wet and the dry detention pond. For the water resources cost estimate, it was performed using research from the Minnesota Department of Transportation. So the construction cost was provided relating to the amount of water quality volume for each individual BMP. And then the annual operating and maintenance cost was listed as a percentage of the initial construction cost. So since a 50-year life cycle was selected to be designed for, the 50-year life cycle cost came out to be about $2.2 million, while the initial construction fee was only about $550,000. So now I'll pass it over to Dana.
Hi everybody, I'm Dana Fish. I'm Fishy Consulting's environmental lead, and I will be presenting you my final design for the Brooks subdivision project. And so here's a bit of an overview of my design. I will be designing a gravitational sewer system that consists of sanitary manholes and concrete pipes. And the flow of this design starts from the east side of Vale Park Road and flows to the west side. And on Old Oak Drive, it flows from the south end to the north end, which connects back into Vale Park Road, and then flowing into that west side lift station to be eventually connected with the existing utilities of Valparaiso, and that is utilized by a force main design, which you can see in the pink line on that side. One of the challenges that I faced with this design was deciding whether or not to add an additional lift station. And as you can see, this is a proposed design schematic, also known as PAT Network for this report, because the natural landscape of this the Brooks subdivision area typically flows downhill from the east to the west on Vale Park Road, but from Old Oak Drive from south to north, it's a bit of an uphill incline. So therefore, with a gravity sewer system, it was naturally getting deeper and deeper as the elevation was getting higher. So my solution for that was to possibly put in an additional lift station. And as you can see, this is not my final design where this is, and I decided to neglect that additional lift station for long-term considerations, as I'll discuss further in the presentation. But in addition to my scope, I was also in charge of, in addition to the lift stations, I was also in charge of designing a bank stabilization method, which will be applied to the Beauty Creek on the west side of the subdivision. So again, I've talked about this previously, but some design constraints and assumptions. I'm just going to highlight on a new assumption that I made in terms of the design for the bank stabilization method, which was it is assumed that the method applied would be able to withstand the creek peak flow, and my method will be applied to about 3,500 foot section, which covers the span of the subdivision area. Okay, so this is the final pipe network that I will be applying for this design. As you can see, Vale Park Road and Old Oak Drive. I don't know if it's super visual for you guys, but there are highlighted in blue here are manholes, and those are typically between 300 to 400 feet apart, and they are located at every turn and bend within the roadway alignment. I decided to design the structures to be inside the road so it allows easy access for maintenance and operation purposes, as well as so that they are in city property lines, so easements wouldn't be an issue with this. And then just a little blow-up, close-up on that connecting structure between Bell Park Road and Old Oak Drive. This is structure 40, and it's a pretty important structure because it's what connects the two pipe lines together. And I'll be showing you more visuals on that. So this is a sample vertical profile of Vale Park Road, and as you can see in pink, that is the proposed roadway from our transportation engineer, and then kind of in the red and blue is the existing grade line. As you can see, these manholes are pretty deep. They're about 30 to 50 feet deep in the ground, and that is due to, as you'll see later, the deep structures on Old Oak Drive. Designing the pipe network was based on pipe slope as well as the functions from AutoCAD, which helped me design sort of the surface elevation, ground elevations, and invert elevations, and I compiled it all in a spreadsheet off on Excel. And so, with that, also to note, on this left side here is the lift station that will eventually connect to the existing utilities with the force main. And then this is that important structure 40 that connects Old Oak and Vale Park Road. This is the Old Oak Drive vertical profile sample. It starts out pretty shallow, and it's important to ensure that the pipes are within 3 to 5 feet below the roadway to ensure frost penetration does not damage pipes. And then this is the reason why the pipe network gets so deep along Vale Park Road is because the slope of Old Oak's Drive's topography just inclines, and with the gravity, it'll just keep going down in order to keep that 1% slope. And this is a sample detailed drawing of the sanitary concentric manholes. Concentric manholes were a standard set by the Operating Utilities Code of Conduct. And so with that, it was a guiding factor for why I chose this design for the manholes. And this drawing is courtesy of standard drawings from Cary, North Carolina. And then onto the force main design. This is just an image of where the lift station on the right side to the existing utilities. It's going to be about 600, length was about 600 feet. And then this is just my force main vertical profile sample of how I calculated using different valves and fittings and transition numbers to eventually help me calculate the total dynamic head. Which then, and this is just a little detail in my design hand calc for what the lift station would look like. And then eventually using that vertical profile that I mentioned before helped me determine the total dynamic head and the pump that needed to be selected and used. And so I'm going with an enclosed non-clog type centrifugal wastewater pump courtesy of the ITT Fluid Technology Corporation. And with this, there would be two pumps within the lift station in parallel just to help with redundancy, as well as if one were to go out of service, the other one would be able to kick on and handle the same amount of load. And so the efficiency of both of these pumps would be about 67%. And then finally, this is the bank stabilization cross-section. I'm using Greenland's vegetative slope-facing system courtesy of Filtrix Technologies, and this is just a cross-section of what it'll look like along the creek. As you can see, there's live staking, the grow stocks, growing media, and at the bottom, limestone base to help with foundational support and stability, and as well as drainage. And finally, I'll just go into a little bit about the cost discussion. The reason why I go with my final design is because the cost to add an additional lift station would just increase operation and maintenance costs, and so over time, you'll just have a higher cost with that instead of just having a high initial cost for deep trenching as the original work would have had. My cost came from estimates from the Arts Means online source, and so those are the major, and also the major drivers of my costs included just the pipe installation and as well as the horizontal drilling and directional drilling. And so in cost comparison, pipe network 4 was slightly higher, so I decided to go with the most cost-effective option. And then in total, the cost estimate for the Greenland's vegetative system was about $669,000. And then this is my total environmental costs in a table version as well. And so with that, I'll transition over to our structural engineer.
All right, thank you, Dana. As mentioned, I'm the structural engineer for the project. What we kind of provided with is the design. You can see in this graphic where it is on the project site. You also got a good look at where it is, the general shape in the parking lot slide on the transportation section. So I went with the structural steel frame building, reinforced concrete floor slabs, second story roof decking to support those slabs, brace frames on opposite corners, and then a reinforced masonry wall around the stairwell and elevator shaft. So this is our floor plan, our architectural layout for the first floor. You can see a couple different areas of this building, and this will carry over, you can see this is where the stairwell and elevator shaft are, as well as these hatched areas, which are the residential areas, which we'll see on the second floor as well. More dwelling spaces on the second floor, as well as the vertical extension of the stairs and elevator. So going into the load charts, the dead loads are generated by all our structural members. The rest were determined from ASCE 716, and the chart on the right sort of describes where we're applying those loads. Namely, the most influential ones were the 100 PSF in the hallways on the second floor, and then the 40 PSF in the living areas, as well as the snow load on the roof. Brief discussion into the snow load. One point of contention with this project was that the exact site for the project, which is the green marker up there, fall into the case study area of ASCE 716. The blue marker down there is about the nearest point to the site that falls under the 25 PSF area, and then that blue line measures at 0.75 miles. So I felt it safe to just consider the snow load for this area 25 PSF under ASCE 716. So this is our structural layout plan for the second floor, or the members supporting the second floor. The red area is where our masonry wall is, and that blue outline is the hole in the slab to carry over to the second floor. Not really visualized on this corner here, the two, let's see if I can point at it with the mouse. Yeah, so this frame here, as well as this frame and this frame are where those cross braces are. And then that is the exact same for the members supporting the roof. We don't have a hole in the slab for the roof, but otherwise everything is the same. So for basic and preliminary design, I used RISA Floor. I input the loads and the patterns, and it generated a design for all the beams and girders in the building. And after checking codes and deflections, I was satisfied with all the beams and girders. Most of the columns were satisfactory as well, but when going into Reset 3D to design for lateral loads and the combined loads, more importantly, there were some columns that did not meet the combined loading section of the code. So I iterated those designs as well as designed channels or double channels for the cross braces to ensure that the deflection limits and combined loading limits were met. The design equations come from the appendix of AISC, the AISC Steel Construction Manual, and just kind of define the limits of the maximum load versus the maximum strength for, again, combined compression and flexural loading. Going into the masonry wall and the slabs and decking I was talking about, the masonry wall is just general masonry units with one number 5 bar per cell. There's a minimum and max spacing on that as well. And then for the steel composite decking, I used Verico W2-36 form lock at an 18 gauge using their LRFD design on the website. They said the span was adequate with a 2-inch depth and the 18 gauge steel. So this CAD drawing comes courtesy of Verico, and then these steel decks will be topped with 2 inches of concrete and then reinforced by a welded wire steel, so just basically a steel grid rather than reinforcement bars. So lastly, going into the cost, using RS means, I input all the materials to a pretty, as close as I could get to exact with a little bit of contingency to ensure we would have enough, and the materials cost itself came out to a little over $700,000, but remaining with the RS means square footage cost estimator, which takes into account a lot more, including namely construction, but then also other big costs associated with a structures project. The cost estimate came out to $5.14 million. With that, I would like to thank everybody for their time and open it up to any questions.
Dana, can you tell us more about this green locks bank stabilization system? How does it work?
Huh?
How does that system work?
Well, it works by, well, as I said before, it's under the assumption that the peak flow of the system would be able, like this method would be able to handle the peak flow, so in that way, it's already assumed that it'd be able to stabilize. That was just one of the constraints I believe you and I talked about before. But to put into more specifics, the different components like the geogrid fabric as well as the soil anchors and the live staking hold hold the geogrid and the grow stock in the media together against the slope of the embankment, and so that's how.
Yeah, on the slope you mentioned it's going to be 1 to 6 slope, and there are you going to be excavating the banks to make it 1 to 6? And if you are to do that, where did you account for like holding soil off-site in this case?
Well, how I came up with the 1 to 6 slope was based off the contour maps from Porter County and that. So I just made the assumption that it was that slope throughout the creek, And in the real life, when you go and visit Beauty Creek, it's not exactly that slope all the way through, and there are trees in the way, there's a lot of stuff already there, and so yes, clean up and as well as, I guess, what you said before would be applied.
Hunter, simple question. You mentioned like the flood control for the swale,
Yeah.
and you're using like the 100 year storm event for the design.
Yeah.
What's the difference between flood control and conveyance in this regard, and what does the VATO ordinance say? So is it like 24-hour plan, 100 year, or if you are doing this for conveyance versus like, I mean, I don't know what you mean by flood control for a swale in this case.
So for the flood control, we use the 100-year 24-hour storm for like the entire site. So like all the water draining would be able to go into the swale and not like overflow.
Why are you doing this for 100 years?
Why? That was the specified design storm from the city of Valparaiso
For conveyance systems?
for flood control. Okay.
It's 10 years.
Okay.
That's a huge, yeah. It's, except, yeah, that's why I'm saying I don't know what you mean by flood control
Well,
for
like-
swale. This is a swale, remember?
Yeah, well, like the pond is designed for the 100-year storm.
Correct.
So all the water that goes to the pond, like in the case of the 100-year storm, I mean, I guess you probably wouldn't have to design the swale for the 100-year too, but since it was already there for water quality and it was already wide and big enough, the depth really wasn't that much of a difference.
Well, I question the design in this case, because if it's designed for flood control, it won't do much for water quality.
Yes.
Check dams.
Huh?
Do you have check dams there?
Yeah, I do have check dams which slows the water and increases water.
So I have a question for water, since you're answering. So I think I asked you this in a previous presentation, but how are you going to maintain water in your wet pond?
Maintain it?
Yeah, because where's the water table? Is it
Oh, yeah. So like the wet pond is gonna be like, with like the like base of it is gonna be like reinforced to make it impermeable so that water does not like infiltrate and then like sits and it can like settle.
Okay, and then related, you did, right, select the plants for the floating treatment wetland?
I didn't select the plants. I'm gonna use like biohavens,
Okay.
floating treatment wetland
Okay.
modules, and I just did like the arrangement for
Okay,
strategic placement so that it wouldn't need as many.
okay. Thanks.
Any other questions?
I would have one general question, kind of a what if.
Okay.
How much easier would your design have been if you did not need to worry about all-wheel drive?
I feel like it would have made it a little more simpler in that way, because I mean, you're neglecting the whole road there, so you wouldn't have that extra lift station and also that pipe network, or that pipeline that connects to the road. I think the cost would be reduced as well,
I think you wouldn't have that major elevation problem.
change, yeah.
I have a question for Alex, Ben, sorry.
Yeah.
So if you can go to the plan, to the elevation that shows your brace frames.
Was it one of the renderings?
The three-dimensional, this one. So first of all, have you checked the horizontal irregularity of the building that might be an issue in your report or in your calculations?
Yeah, I have way too far. I'm sorry, give me one moment. I did break. So this wasn't included, okay, now we're at the meeting. I'm so sorry.
Sorry.
Here we go. Okay, so this is actually from ASE 716, defining the horizontal regularity and how.
So you also have been in like slides in the presentation, or maybe it's my fault, I didn't see this one.
No, this is extra. I
this
didn't
is
put it in the main presentation
Oh,
for just time constraints, but yes. This is the table from ASE 716. We are in seismic design category B, and it falls under this this category of all other structures and just basic.
One more question about that slide, the elevation that you have. You decided to put the brace frames at all of them at two corners, right?
Yes.
So it's kind of unsymmetrical arrangement. This might cause the center of the rigidity to have like some eccentricity from the center of the mass and cause like some torsional forces. Have you checked that?
I have not.
Okay. So that was